So we talked in a previous section in Chapter 11 that a characteristic of a star, one of the characteristics of a star that's important is how much energy is it pumping out per second. Remember we said that in the core of our star, the sun, we have nuclear fusion going on, and that's the case with the cores of other stars. So we're going to talk more about that. But in order to understand or to qualify the wattage of a star, we need to understand how far away the star is, because its brightness that we see is dependent upon both how far away it is and its luminosity, how much energy it's putting out. So bottom line is we can use parallax, the wiggle basically of stars, a nearby star, against the background stars. We can use this parallax of a star as we orbit the sun to gauge the star's distance. And this is why I'm introducing this section on parallax. And we've talked about parallax before. I'm going to show you some animations that your author puts out there. Kind of fun, see what you think. So remember, parallax is kind of the wiggle or the movement of a nearby object relative to background objects as the observer moves. So here we have two frames of reference. Down at the bottom you have a guy looking through a camera, and he's moving, and down there and up there at the top is what he sees through his camera. Okay, so here we go. We're looking kind of at a nearby man, a little farther away, grove of trees. In the distance we kind of see, to me we see two mountain ranges. We see kind of a smaller mountain range, but that's pretty darn far away, and then behind the smaller mountain range we see the greater, higher mountain range. So I'm going to go ahead and let him proceed from left to right. And notice that the relative position of the guy in the trees is changing, and the background. Okay? But notice that these two far away mountain ranges don't change. And so only if an object is relatively close does it change against background objects. That's parallax. Well, if we apply that to stars now, we're going to look at the parallax of a relatively nearby star compared to the faraway stars as the Earth orbits the sun. Okay, so here we have 3 months later, September. 3 months later, December. March, and then back to June. Okay, so I'm going to kind of want to highlight a few things. I'm going to move this cursor over. So June. Now, we have a relatively nearby star, red star here, and you can look at this, see it wander against the background stars from June, 6 months later, to December. Okay, I'm going to go back and forth. June to December. Okay, June to December. Okay, notice that the faraway stars, just kind of like our mountain ranges, I mean, they don't move, but this relatively nearby star does move. And there actually is a limitation to gauging distances of stars this way. And that's about, I'll tell you in a minute what that is. One more, I think just one more. Two more actually. These are all so good. All right, now in this case, it's going to kind of, notice this is kind of like we're going to call it a blink comparator kind of. You see this field of stars 6 months apart, and the star that's moving is the nearby star. It's the red star. Now, the way this little applet works is I can change the distance between us and that relative nearby star. So that star is 1 light year away. What if we bump that star up to maybe 5 light years away? 10 light years away. You see what's happening is the wiggle, as that star gets farther from us, its wiggle or its displacement, here in a minute we're going to call the arc seconds that star moves 6 months apart is less and less as the star gets farther away. Let's go ahead and bump that to, now we're about 20 light years. Now that star is eventually going to become one of the background stars, and you're not going to see the wiggle. Okay, so there is a limit to if the star becomes too distant, we're not going to see any parallax. And can you remember we talked about angular resolution? And so remember, so this is where angular resolution would come into play. The better the angular resolution of our telescope, the more we're going to be able to see those subtle angles. I do have one more for you. Okay, and this one it's just animated. So from left to right, we have a picture 1, and 6 months later, picture 2. And if you're looking at those, it's kind of hard to see what stars wiggled or what stars moved. And then if you look down at the third box down here below, what they've done is they're kind of blinking back and forth. Picture 1, picture 2, picture 1, picture 2. This is a type of technique called kind of a blink comparator. And actually, this is how they find a lot of objects in the sky that move against background stars. So the way this works is if I were to click here, this green star, it tells me that the angle that it's wiggling, the angle we say it subtends, is 0.5 arc seconds. And that's an indication of how far away it is. And I'm going to show you the formula here in a minute. This brown star down here, it has a larger angle. It subtends. And so the larger angle means it's farther away. Just randomly, let me click on this red star. Notice that there's no wiggle. It's not changing its position in the sky. So we can't use this technique to determine how far away that red star is. So I think we had this figure earlier. But I've mentioned the angle that object wiggles in the sky or subtends. We're going to call this the parallax angle P right here. And so actually, if we're kind of looking at from left to right, you kind of see that we have this yellow star that's a nearby star, and it's changing its position against the background stars. Can you see that at the top here? And the wiggle actually over a period of 6 months is actually twice the parallax angle. Okay, so once we get that parallax angle, are you ready? Here we go. Oh, before we get to that, I'm going to tell you what to do with that parallax angle, how to get distance between us and that nearby star. But before I do that, I need to explain what a parsec is right quick. We talked about what a light year is, and a light year is the distance that light will travel in 1 year. Light year is a distance, remember. And a parsec is actually related to a light year. A parsec, abbreviated PC, is greater than a light year. You can see it takes about 3 1/4 light years to equal 1 distance of a parsec. And in order to get the distance of a parsec, what we need to do is to look at an object that's 1 astronomical unit away. We need to look at an object, and that object's diameter, it needs to be 1 astronomical unit. And then we set that object way away from us so that in our sky, the angle it subtends, that object that's 1 astronomical unit, is 1 arc second. And then in that case, the distance that we have relocated that object is 1 parsec. So if you're like me, I had to double check what an arc second is. The word arc just means that the object is what we say subtending, or that's kind of how big it is in the sky. But if we focus on the term second, what is a second? Well, you guys know in a circle there are 360 degrees. In 1 degree there are 60 minutes. In 1 minute there are 60 seconds. So there are what? 3,600 seconds in, no, that's not right. So that's how it breaks down. So let's go back now. Once you find that wiggle, that parallax angle, how does that translate to understanding the distance to these stars? Now remember, this is limited to only nearby stars. In terms of, it depends upon the quality of your telescope as to what sort of angular resolution you have with that telescope. But for land-based telescopes, they say that you're limited to about 100 parsecs. And if you're using a telescope that's in orbit about the Earth, you can gauge the distance to stars to about a distance of 150 parsecs. So once you get that parallax angle, what you can do then is take 1 divided by that parallax angle, as long as that angle is in arc seconds, and then you will have the distance between us and that star in units of parsecs. Well, so let's say you're not a parsec sort of person, you want the distance in light years. Well, you can do that by simply taking that number and multiplying it by 3.25 to get the overall distance in light years. So this is how we get the distance between us and relatively nearby stars by looking at parallax. And remember, the reason that we even care about distances to stars, well, there's a number of reasons, but one of the things we can do, if we have the distance to a star, we can square that term, multiply it by 4, and then times the number pi, and then we can multiply it by the brightness, or what I call the apparent brightness as we see it here on Earth, and then we have the star's overall wattage, or the star's luminosity. And its luminosity is going to be a key player in understanding the general size of the star, in understanding that star, how it's living its life, and what stage it's in. So these are, distance is an important characteristic of a star, so is luminosity. And remember, brightness is what we see it here on Earth.